Hello, uh, welcome to this part. So in this part, we are going to discuss another parameter that we generally consider while designing the laterally supported beam, and that is web buckling and web crippling. Well, what is web buckling and crippling? That we need to understand first. Basically, if I make the diagram of I section, say this is the I section, and longitudinally it will look like this, and this will be the support. Say this is the support, and this is the flange line of this I section, and below also. Now if there is a load like this one, say this is the concentrated load W, and because of this load reaction will be there on both sides. So below this load, below this concentrated load, the beam may, I mean the web, this part is web, the web may buckle. So if in the cross section I will show you, this web may, under the load, this web may buckle like this. Similarly, uh, at the same time, this web may buckle, or another parameter can also occur, which is uh, it may cripple like this. Now this is the load like this one, and below this load, it just below this load, it may cripple like this. Sorry, like this. It may cripple like this. So this is web crippling and this is web buckling. So we need to check our beam while we design our laterally supported beam. We also need to check our beam for these two criteria also, like web crippling strength of our beam and web buckling strength for the beam. So web buckling strength depends on again flange to thickness of web ratio. In case of like you can see this web is buckling. So what is happening actually is this vertical part of the beam, we can assume this vertical part as a small strut, and this small strut, because of this vertical load, it is actually buckling like this. Okay, so now we will look into this in more detail, how it will be occurring, and how do we check the strength of beam under web buckling and under web crippling. So generally, when there is a heavy load or a reaction concentrated on a short length, produces a region of high compressive stress in the web, either under the load or at the support. As I said that just below the load, the region becomes very high stressed, or we can say that it will be critically stressed. So in that region, the beam web may buckle or it may cripple like this. So because of this load, it may buckle like this or it may cripple like this. So as I said, this may cause web failure such as web crippling or web buckling. So in that scenario, what we are going to do is we are supposed to find out our web crippling strength and web buckling strength, like how much load this web can take, or how much load this web can take under the crippling load. So basically now we are going to find out our beam strength in terms of crippling, in terms of buckling, web buckling. So first we will find out the web buckling strength. So web buckling strength is again dependent on the reason. Like web buckling strength can be easily calculated like this. So FWB is referred to as web buckling strength, and it will be B1 plus N1 and whole multiplied by TW into FCD. Well, this FCD is the same as we have used in the design of compression member. This is the same FCD. Now, why we are using this FCD? Because our small web, like this beam web, this web is acting as a compression member. because as I said, this small web can be considered as a strut, and struts are compression member. So that is why, to find out the web buckling strength of this web, first of all we need to consider this web as a vertical member, as a strut, and then we will multiply the design compressive stress, which is FCD, and it will be multiplied by the area of cross section, which will be the effective area under which the maximum stress is occurring, maximum compressive stress is occurring. Now, what is this B1 and N1? How do we find out that? That we will see through the uh, diagram. So this formula is when there is a reaction. Basically, at reaction also there may be a concentrated concentration. I mean, the reason may be concentrated. Similarly, below the concentrated load, it will be B1 plus 2N1. Now, I'm sure you are not able to understand this, but now I will be showing you the diagram and then things will be clear. Now, in this diagram, you see this is the beam, and this beam is supporting a secondary beam, secondary I section. So width of flange is B1, and you can see this beam is taking, I mean, the load of this beam can be considered as concentrated vertical load, and this load across the depth of beam, this is also, this is main beam. So because of this load across the depth will disperse at 45-degree angle, and we know that maximum buckling in the web will occur at the mid. You can see buckling will occur like this. So maximum buckling will be at the center. So at the center, this load will disperse at 45-degree. So at this point, how much length is this? This one is the effected length. So in this length, up to this length, the stress will be highly concentrated. So the length of this one will be B1 plus 2N1. Now this one is N1 and this one is also N1. So that is how we find out. So B1 plus N1 will be under the reaction. If under the reaction also it may buckle. So in under the reaction there is no dispersion. The dispersion is along one side only. So that is why we are taking the length of dispersion as B1 plus N1. While when there is a concentrated load, the load will disperse from both sides, and in that case N1 value will be on the both sides. So this one is also N1, and this side also there will be N1. So this is how this formula forms. So this is the length of dispersion or the effective length. And when we multiply this effective length with the thickness of web, then we get the cross-sectional area. And when we multiply this cross-sectional area with the design compressive strength, then we find out the web buckling strength. So the closer view you can see here. So this closer view you can see here. So reaction is, as you can see, beam is resting on the seat angle, and seat angle is offering this reaction, which is say R, and against this reaction is actually dispersing at 45-degree angle. So at the mid, this length is effective. So up to this length, web buckling may occur. So which is just above the support. So web buckling may occur between this length B1 plus N1 length. So B1 here is the length of bearing. So what is the length of bearing? That will be the B1 value. Similarly, in this case, B1 is the width of flange when we find out the web buckling strength under the concentrated load. So this is how we find out the buckling strength. Now, the point is, how do we find out this FCD now? Because FCD is dependent on the cylinderness ratio. So that we will see. So here TW, in this formula, TW is the web thickness, FCD is the allowable compressive stress or design compressive stress when we assume web as a web strut. Now FCD is dependent on the lambda value and the grade of plate, which means Fy value. So Fy is, we already know it will be 410, but it will be dependent on lambda, and lambda value, we know lambda is called effective length upon minimum radius of gyration. So I am writing here Le upon minimum radius of gyration generally occurs along the y-axis, so Ryy. So that we will see how do we find out this lambda value. So effective length generally, as I said, that we are taking the case of I section. So in the I section, web is in between the flange. Web is in between the flange. So that is why we will assume that the flange will be fixed end from both end. And in that case, the effective length, say this is the D. So effective depth or effective length will be equals to 0.7 times of D. So you may remember, in case of fixed column, the effective length will be 0.65 L. So in the same line, we are taking here 0.7 times of D. Now, once we find out the effective length, then we need to find out the minimum radius of gyration also. D is the depth of strut in between the flange. So therefore, the slenderness ratio can be calculated as you can see here. So slenderness ratio will be Le by Ryy, and Le, we have just find out that effective length of web will be taken as 0.7 times of D, and Ryy will be the minimum radius of gyration. Well, D is, again I'm showing you, if this is the I section, so in that case this will be the D. So Ryy, we know Ryy is the radius of gyration about the y-axis, and radius of gyration can be calculated by using this formula. We have used this formula earlier also when we were discussing about the compression member. So Iyy upon A. Now Iyy, now just imagine this web only. I'm separating here, and thickness is TW, and this is the depth, which is D. So Iyy, y-axis will pass along this one. So Iyy will be, I mean, you must be aware of the moment of inertia formula, like Ixx, we call it TD cube by 12. Similarly, if we need to find out Iyy, it will be opposite to it, which becomes yes. So Iyy will be D T cube by 12. Sorry, I have written here wrong. This will be D into TW cube upon 12 into area. What will be the area? Area of web will be TW multiplied by D. So TW into D, and this will be under the whole square root. So TW will be cross and D will be cut from here. So ultimately the value will be TW by 2 root 3. And when we put this value in this formula, then we get this one, which is approximately equals to 2.5 times of D by TW. So we can say that the slenderness ratio of the idealized strut or web is taken as 2.5 times of D by TW. So if we get the slenderness ratio by using this formula, then we can easily find out the FCD value by using the table 9 and table 9C. So using the table 9C of IS code, we can find out the FCD value. So now we will find out the uh, web crippling strength. How do we find out web crippling strength? So again, we need to see web crippling occur just below the load or above the reaction. So based on that, load dispersion is again a criteria. Uh, In the previous case of web buckling strength, we assumed that load will be dispersed at 45 degree, and here the load will be, we assume that load is dispersing, you can see here, the load is dispersing at this slope 1.2 is 1 is to 2.5. So in that case, you can see here, uh, if it is the reaction, now below the reaction, just I mean above, just above the reaction, web is crippling. Now web start crippling just at this point, so load is dispersing at this angle up to this point. So this is 1 is to 2.5. Now this length is r1, which is called root radius. This root radius value for all the sections is available in the steel table, so we can find out this r1 value. So just above the r1 value, web crippling will occur. Similarly, then this is the thickness of flange. Now the web crippling strength will be taken as B1 plus N2 into TW into FYW. Fy is the yield strength of web, TW is the thickness of web, B1 plus N2 is the effective length, like up to this length, web crippling may occur because the load is dispersing at this point. So up to this length, the crippling may occur. So this kind of crippling may occur up to B1 plus N2 length when in case of reaction, in case of support, and if there is a concentrated load like this one, in that case again, uh, load will disperse in this direction, load will disperse in this direction. So in that case, there will be 2 times of N2. Now here I have taken only N2 because in case of support, only one side is load dispersing, other side is not dispersing because that is restrained. So the formula is similar to the strength that we have seen in case of buckling. The only change is this value B1 plus 2 B1 plus N2 and B1 plus 2N2. So this we can easily calculate, because now if we know the slope, we can find out what will be the value of N2, and N2 will be equals to 2.5 times of TF. TF is the thickness of flange and R1 is the root radius. So you can see D1 is basically the sum of a root radius and the thickness of flange. So this N2 value will be equals to this one. Similarly, TW, which is the thickness of web, and FYW is design yield strength of the web. So this I have already discussed. So now in the next part, we will be discussing about the design steps that we generally use to design the steel beam. Thank you.